Oh, it's 11:51. Great. Okay. I hope you did well, but no matter what, congratulations on finishing the second midterm. Well, the semester is almost over. We have 3 more weeks left? Was this? I think so. And then there's the final and we're done. Okay. So today we're extending the concepts of mass, position vector, linear momentum, angular momentum for a rigid body. Let me just move this desk. Sorry about the noise. Okay, so for one particle, a particle has a mass and position vector with respect to the origin Ri or Xi, whatever we choose to call it. Linear momentum, G is m times v, its mass times its velocity, and its angular momentum we can calculate it about any point, about point O, the origin, for example, that's r cross mv, about any point P, that's r minus rp cross mv. V is the velocity of the particle again. So are we okay on this part? All the quantities for a single particle. And then for a system of particles, we generalized all these concepts. We said that for a system of particles, each individual particle has all these. But then for the system, we can calculate the total mass of the system, which is the sum of the individual masses. The center of mass of the system, the position vector of the center of mass, is kind of the weighted average of the position vectors of all the particles. What's the weight? The mass of each individual particle. So the sum of mi Ri over the sum of mi. We define the linear momentum to be of the system to be the sum of the linear momenta of the individual particles, the sum of mi vi, which turns out to be the total mass times the velocity of the mass center, the center of mass of the system. And then the angular momentum of the system is the sum of the angular momenta of the individual particles. And we can write the angular momentum about point P or about any point. Okay. Now we need to generalize all these concepts for a rigid body. So what do you think the main difference is going to be between a system of particles and a rigid body? Yes?
The distance between particle and system.
Yeah, exactly. So for a system of particles, we have discrete particles, right? There's a distance between them. But for a rigid body, how do we call the particles for a rigid body? They're not discrete, they're continuous. Exactly, there's a continuum of particles. So instead of summing over individual particles like we do for a system of particles, for a rigid body, instead of summing, what do we call a continuous sum? So for a system of particles, for example, to find the total mass, we sum the individual masses. But for a continuum rigid body, instead of summing the individual masses, what do we call summing continuous masses? What's a continuous sum? Yes, that's an integral. So instead of summing, we're just going to integrate, but the concepts are still the same. So what are we integrating over? We're integrating over dm, differential masses that are composing the rigid body. So this rigid body, I'm going to call it P. That rigid body is composed of differential masses. We can think of them as small particles. I'm going to call that dm. And then the total mass of the rigid body, instead of summing, I will integrate. So n is the sum over the body of the individual masses. Does that make sense? With me so far? Great. Now, what do you think the expression of the center of mass is going to be? So we're going to take some point. That point is going to define to be the center of mass. How are we going to define it? Any ideas? Ideas? Yes?
Like using the integral over ey dx.
Exactly. The integral of what?
Of the differential masses.
Exactly. So the position vector of each differential mass times the mass over dm. So what is R here? We have an origin. R is the position vector of the differential mass, right? And we're summing R dm for each possible differential mass of a rigid body. So you can think, that's a crude way to think about it, but you can think of the body as a bunch of differential masses, and we're summing RDM, 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 RDM for each differential mass. So R is the position vector to the differential mass dm, and then we're summing that over all the possible dm's of the body. And each dm has a different position vector at each instant. Okay, so R is the position vector relative to the origin. Okay? Then the linear momentum of the system for example, G, that's going to be also the sum of the linear momenta of the constituents, but instead of the sum, I have the integral over the body of, can someone guess what the integrand is? V dm. Raise your hand if you agree, if you think that's all right. Yeah, it makes sense. It's V dm. What is V here? The velocity of what? The individual dm, right? So that's the velocity of dm. Kind of like here, each dm has a certain V. Here, each dm has a certain V. So for each dm, I'm multiplying dm by V and then summing. That's kind of what's happening. Okay? So that's the linear momentum of the system. We can express that as the linear momentum of the center of mass, where m is the total mass here, and Vc is the velocity of the center of mass. Okay, how did I go from here to here? Well, MVC is m drc by dt. The velocity of the center of mass is the derivative of the position vector of the center of mass. So that's m and then d by dt. Well, m times rc is the derivative over the body of r dm. Do we agree? Are we okay with this? Okay. Now, and then what we did is this, we put the derivative inside and we got the integral over the body of v dm. So then mvc is the integral of v dm, which is g. Now, mathematically speaking, I did some mathematically incorrect tricks here because I flipped the d by dt with, put it inside the integral, and then technically the boundary of the integral may be dependent on time. But for now, I won't go into this. But just know that I'm not totally mathematically correct in flipping this. For more details on this calculation, you can check O'Reilly's textbook. He has that. I'll explain. Okay. So then the linear momentum of the system is the integral of v dm, or mass times the velocity of the center of mass. Questions? Questions so far? Okay. Now we come to the angular momentum of the system. Okay. The angular momentum of the system, can anyone guess what the integrand is? Yes? R cross what? Not quite. It's the discrete version of this. Right. But since I'm calculating the angular momentum about point P, then I'm going to add the R minus RP cross V dm. So that's basically here the angular momentum the angular momentum of dm about P, and I'm summing that for all the possible dm's. Do we see how that's the angular momentum of dm? Right, because the angular momentum of a particle is r, the position vector of the particle, minus rp, where I'm trying to find the angular momentum about, cross the mass of the particle times its velocity. Okay, so that's the angular momentum of the particle about P. If I want to calculate the angular momentum of the particle about the center of mass, what would the expression be? There's going to be a slight change. What would that be? Ideas? It's still an integral. There's just one letter that's going to change. Instead of finding the angular momentum about P, I'm finding it about C now.
So would RP change to RC?
Yeah, exactly. Instead of R sub P, it's going to be R sub C. So we're calculating the angular momentum about point C. Okay? Great. Can we relate the two? Yes, we can. We did that for a system of particles. Let's do it again for a rigid body. So what we're going to do is, I'm going to start with this, and I want to express this in terms of hc. So I'm going to rewrite the integral. I'll have r, I'll add minus rc plus rc minus rp cross v dm. And this should equal to hc plus something. Please take a few minutes and work on this in pairs. Show this derivation pretty quickly. If you need papers, I have papers. Here we go. Okay, take 2 minutes. We won't have a lot of time for this. Quickly. When I see sleepyheads, I get the urge to give you quizzes. So it's kind of your fault, huh? That's not how it works. To get good knowledge, you need to sleep well and eat well and have a balanced life overall.
Thank you.
Oh, you have paper. Yeah, come on. Yeah. Yeah, you can ask your partner. Come on.
Thank you.
you need to show that it's equal to hc plus something, right? Okay, let's do this together. So I'm going to erase this part. What's the first step here? Ideas? Yeah, divide and distribute. So I'll get R minus RC cross V dm. That's my first term. So it's this crossed with that. And then the second integral is going to be this crossed with that, right? Plus the integral of RC minus RP cross V dm over the body. What's this first integral equal to? HC. What about the second integral? Can I simplify it? There's something about, do C and P, do they depend on the particular dm we're integrating about? No, right? So C and P are constants with respect to this integral. V depends on the particular dm, right? As dm changes, V changes. But C and P are not going to change if I change dm. So they are constants with respect to dm. So I can take them outside the integral. I can write RC minus RP because the integral of V dm. What's the integral of V dm? VC. MVC, right? So then I have that HP is equal to HC plus RC minus RP cross MVC. Right? Sounds good? Okay. Yes.
Is the angular momentum for the center of mass not just, or like, that's why I was asking if you still need an integral, because isn't it equal to the mass for the mass of the whole system?
Say again. I think you have a great question in there. Do we always need to integrate to find the angular momentum? Is that your question? Do we always need to evaluate an integral?
Shouldn't the angular momentum for the center of mass be the same as the one for the whole, like treating it as a particle at that point for the whole system?
No, not quite. Because when we're calculating the angular momentum depends on the mass distribution of the body. So all the particles dm, their velocities, and then their mass distribution relative to the particle p. So you cannot consider the whole body to be a particle when it comes to angular momentum. So for linear momentum, yes, the linear momentum of the system is equivalent to some equivalent system with the same total mass and with velocity. Okay, let me say that again. The linear momentum of a rigid body is equivalent to the linear momentum of a particle whose mass is the total mass of the rigid body and whose velocity is the velocity of the mass center of the rigid body. For the angular momentum, that's not true. Yeah. But then your other great question in there is that, do I have to evaluate an integral every time when I calculate the angular momentum of a rigid body? And the answer is kind of. We're going to say that for, well, let us see. We're going to start with HC, which is equal to the integral over the body of R minus RC plus V dm, and try to manipulate this integral so that hopefully our answer is no. We don't have to evaluate an integral every time when I calculate the angular momentum of a rigid body. Okay, so we're going to start by saying that for any material point on the body with velocity v, I can write that v minus vc is equal to omega cross what? Exactly, minus rc. Okay, so that again, r and v are the position and the velocity vectors of the differential mass dm. Okay, so I'm going to replace v by vc plus omega cross r minus rc dm. No funny business yet. Any questions? Okay, and I'm going to separate this integral into two. The integral over the body of r minus rc cross vc dm plus the integral over the body of r minus rc cross omega cross r minus rc dm. Did I make any mistakes? Questions? Okay, we're gonna stick with the primer's notation, and we're gonna call this vector lowercase pi. Right? It's the same vector. So basically what it is I have a rigid body, I have my origin, I have a differential mass dm, and I have the position vector r from the origin to the differential mass dm, and I have the center of mass of the body, and this position vector is rc. Now the position vector of r with respect to c, I'm calling it lowercase pi. Okay? So then pi, we'll introduce maybe a basis later, but we'll call it xex plus ey plus z for later use. Okay? Questions? Okay, so now we have two integrals, this guy and this guy. Right. What is the first one going to be equal to? You did that as a quiz, but instead of integral, you put a sum. Mm-mm. The first integral is equal to what? Not HC. Well, C does not depend on dm, right? So I can take it outside. So I can write this as R minus RC dm cross VC. Now, what is this equal to? This part specifically. Mm-hmm. Yes, then what will it be? I didn't hear you. What will it be? Guys, come on. This integral, if I split it into two, that's the integral of R dm minus the integral of RC dm. Now what is it equal to? RC, I can take it outside. That's M RC. Now what is this equal to? So what is this integral equal to? We did that as a quiz. We need to become quick at this stuff. Okay. Now this second integral. Ooh. I'm just gonna take the integrand pi cross omega cross pi. Okay, I want you to Google the backup identity, please, and tell me what this is equal to. Who can Google it? Backup. What is this equal to? Yes.
A cross B cross C equals B A dot C minus C A dot B.
Like this? Did we get same results? Hopefully. Okay, so we can simplify this cross product. Instead of having A cross B cross C, I can write B, which is omega, A dot C, which is pi dot pi, right? Minus C, which is pi, A dot B, it's gonna be pi dot omega. Is that right? Did I make any mistakes? Raise your hand if you think I'm all right, if my calculations are okay. Okay, I have a few confirmations. Cool. Okay. Now, what does this remind us of when we have pi dot omega along pi? Does this remind us of something? Yeah, you got it. A bun B applied to C, that's equal to B dot C along A, right? So how can I write this as a tensor product times a vector? Pi dot omega applied up to pi, how can I write this as a bond product, a tensor times a vector? Here's the formula in front of you. Yeah. Pi 1 pi applied to omega. Right, that would be pi dot omega along pi, which is, that's correct. So we wrote this as a tensor multiplied by omega. I will write this now as the identity tensor times omega, and then pi dot pi is just a scalar. So then I will write that as pi dot pi times the identity minus pi 1 pi all multiplied by omega, right? And I can do this applied to omega. So that's a tensor minus a tensor. I can subtract tensors, no problem. So again, what is I? That's the identity. Tensor, meaning I times omega, or I omega is what? If I is the identity, I omega is what? Just omega. Perfect. Okay, great. That's awesome. Let's go back and put that into our integral. So now, so far, we have that HC is equal to the integral over the body of pi minus pi 1 pi dm times omega. So what did I do? I took omega outside the integral because omega is a property of the whole rigid body. It does not depend on the specific dm. So omega will not change depending on which dm I'm considering. It's not r and or v. Omega is the property of the whole rigid body. Did you guys take mechanics of materials? No? This tensor is what we call the inertia tensor. Okay, and we're gonna call it IC. So it's not the identity because it's not just I, it has the subscript C. Sorry, superscript C. So that means that that's the inertia tensor above the center of mass, about C. And I could have IP, the center of mass, the moment of inertia, not about the center of mass, but about point P. So we have that HC is equal to IC omega. This is a very cool equation where AIC is the integral over the body of pi 1 pi I minus pi 1 pi dm. Okay, that's great. And then this integral, well, let us see what the matrix representation of this integral is going to be. So what the components of this are going to be in kind of in the Cartesian basis. So let's do this. Okay. Okay. So I have IC is equal to the integral over the body of pi dot pi I minus pi 1 pi dm. Okay. And we said that we're going to express pi in the Cartesian body fixed spaces as pi is equal to xex, or maybe I'll write that on this side. Pi is equal to xex plus y ey plus z ez, where ex, ey, ez is the body fixed spaces. So let me ask you a question. For some differential mass dm, do the quantities x, y, and z, do they change in time for some fixed dm? Do they? So this is my pi. This is the center of mass c. This is pi. As the body rotates, ex and dy and dz co-rotate with the body. So will the components of pi on this co-rotational basis change? No, they won't, right? So x and y and z are fixed in time for a certain dm. Fixed for a fixed dm. Okay, this information is going to become useful in a bit. For now, I'll have that this I can write as pi dot pi is equal to x squared plus y squared plus z squared. The matrix representation of the identity tensor is the identity matrix. And then this, the matrix representation of this is equal to x squared, xy, xz, xy, y squared, yz, xz, yz, and then z squared. Okay. So that's the matrix representation of these, and I'm gonna call the components of this ICXX, ICXY, ICXZ, ICXY, well, ICYX, ICYY, ICYZ, ICXZ, IZX, ICZY, ICZZ. Okay. So then if we take one component, for example, if I consider just IXX, if I consider just IXX about C, what is it equal to? The integral of what? IXX is the first component. So that's going to be equal to x squared plus y squared plus z squared minus x squared. So that's going to be the integral of y squared plus z squared dm. And then if I consider a typical product of inertia, ICXY, I can write this as the integral of 0 minus xy dm. Have you seen these before, any of these? Doesn't seem like it. Okay, great. We'll continue from there on Thursday. Actually, I might send you a few videos to watch, then have to prepare us for Thursday's lecture. Have a good rest of your day.